Okay, so hi everyone, welcome to the seminar on optimization algebra and geometry. We are pleased to have Elizabeth Gross from University of Hawaii. She's going to talk about model selection for Gaussian mixture with numerical algebraic geometry.
All right. Thanks, and thanks, Ali, for inviting me. Let's see, we have James and Jeffrey. I'm trying to think about talks as me being a person talking to other people. So it's nice to see everyone who's here. So I really want to talk about, I'm going to look at our problem that comes in statistics, which has to do with model selection for Gaussian mixtures. And I will really come from algebraic statistics. So in algebraic statistics, I saw the talks that you guys have had in this seminar, and I think you've had quite a few people from algebraic statistics, so I don't need to give my normal spiel. But the main thing is, right, we use algebra and geometry and combinatorics to try to answer statistical problems. All right, and so some of this is also playing around and seeing what we can do. And there's a nice interchange between, the world of algebra and the world of algebraic statistics, where we say, oh, okay, there's some things that we can do over here, but we might need some more algorithms and some computational algebra results to actually make it work. And so you can think about this sitting in that interplay there. Okay, so the main focus of my talk is going to be these Gaussian mixture models. And so, what are they mainly used for? One of the things that they're popular for is clustering. So this is a picture, and you're going to see the animation that I shamelessly stole from Wikipedia because I like the animation, and we'll see how it goes along. But there's lots of ways to do clustering, right? You have a lot of different supervised methods and unsupervised methods. Model-based methods, the really underlying technique that would be there is fitting a Gaussian mixture model. And so that's what I want to introduce today, and the different problems that are involved there. So what is the Gaussian mixture model? Because I think Ali was also saying some people come from math. So, a multivariate Gaussian distribution is, you can just, everyone's familiar with our, one-dimensional Gaussian distribution. But in the multivariate case, you're going to have two parameters. You have your mean vector, which is sort of telling you the center of the distribution down here. And then you have a covariance matrix. So my covariance matrix for each of the distributions are going to be sigma I. And this covariance matrix is sort of telling you the shape of the mound, right? Is it going to be long and sort of skinny, or is it sort of very tall like this? So that covariance matrix is what's telling you the shape. And so if we have a single multivariate Gaussian, people feel very familiar with that. And all we're doing in a Gaussian mixture model is we're taking a weighted sum of these multivariate Gaussians. So a k-component Gaussian mixture model, I'm going to take basically k different Gaussians, and I mix them. So whenever we take a weighted sum in statistics, we say that we're mixing it, right? So the sum of these omega i's is going to sum to 1, and that ends up being our Gaussian mixture model, or sometimes our density. And so that's what we want to look at today. And so what are the statistical challenges with Gaussian mixture models? So the first one is parameter estimation, which on my next slide I will talk about the EM algorithm that aims to answer this parameter estimation problem. But the other thing that's hard is figuring out actually how many components that you have. And that's going to be our focus today. And so to sort of summarize, these two different things. Oh, and I'm doing this on my iPad, so the illustration won't be as cool, but that's okay. So how do you do parameter estimation for these things? You use the EML algorithm, and the hard part is that you have information that you don't know. So your data might look like this, where let's imagine that not having colors, they're all black, and this is my data points. I actually don't know a priori which data point might belong to which Gaussian component, right? And so I have this missing data problem. And so one thing that works really well when you have this missing data problem is the EM algorithm. And then how it works is it's going to alternate. It's going to pick like a labeling, right, of each of my data points. And then what it will do is it will estimate the parameters. And so for us, the parameters are that mean vector, and the mean vectors for each distribution, and the covariance matrix for each distribution. And so it's going to estimate that. And then once it has that estimation, then it's going to assign a new labeling to each of the data points. And it's just going to go back and forth like that. And it can be actually quite effective, right? So we can see even in one step, we're already seeing some good clustering going on. And this is going through step by step. And as we're going back and forth between labeling and estimating the parameters. All right, so this is a pretty effective algorithm. The problem is that it does require you to tell it how many components that you have, right? And so, if you're going to input one, do I have do I have 2 components? Do I have 3 components, 4 components, 5 components? So the model selection problem with these Gaussian mixtures is actually, how do you determine the number of components K here? Okay, because that's what we want to sort of feed in order to do parameter estimation. And that's what we'll focus on. Okay, I have a couple more slides where it gets a little bit better. Okay, if I'm not doing it on my iPad, you see that it ends up starting to converge. All right, so now let's look at model selection. So that's the model selection problem that we want to use. So that we want to see how we can use computational algebra to solve. So, in algebraic statistics, there's a lot of different problems that we've looked at that have to do.
Sorry, one question.
Yeah.
Maybe I missed it somewhere, but so this is like a 2-step process, right? So in the first step, you estimate the parameters of the Gaussian distribution, right? Is that right? And then
once you have parameters. So once you have parameters, then you can estimate the labels. And so you hit the labels, and then once you have the labels, then you get a new estimate for the parameters, and you go back and forth like that.
Okay. And then the second step is to find the number of components, right?
Yeah, so that's just like, so that iterative approach is just the EM algorithm. That's something that already exists. The input that you have to put, though, is the number of components. And we want to focus on that number of components problem. It's not going to solve that number of components problem.
Okay.
And so that's going to be the question that I'm going to call model selection. But in algebraic statistics, we've looked at a lot of different types of model selection problems and have quite a bit of success looking at it from using tools from algebraic geometry, and especially numerical algebraic geometry. So how did this problem actually come to me? I wanted to add a little bit of background. So my collaborators here are Adele Adini and Sarah Shrinkum. And basically they had come to me because they had seen this other paper that we had done for biological systems and model selections. And so they wanted to see, okay, can we take the ideas that we had there and apply them to this problem? And so we can really see what we're going to do here today as playing around and seeing how we can adapt some of the tools that we used before. And so the main ideas that come from this paper with Brent Davis, Kenneth Ho, Daniel Bates, and Heather Harrington is there we were looking at biological systems, but you have, the biological systems that we were looking at there, they actually weren't, the models were not statistical. They are polynomial ODEs, but we are assuming that we have steady state data. And then what happens is you have these polynomials. And the moment that you have polynomials, right, we coming from like the computational algebraic geometry world is whenever you have polynomials, you have a variety. And then you can start using these tools that we like so much. And so there, in this biological systems problem, we were really trying to minimize the distance between the data and what we were calling the model variety. And this language, we're going to have to, say what that means in our context when we're thinking about the Gaussian mixture model case. What is going to be our data that we're going to use and what's going to be our model variety. And we're going to have to play around because it's not going to be as easy. It's not going to be as easy to see as in these biological systems problems. But that's the main idea. And so if I do want to minimize the Euclidean distance between data and some algebraic variety, then this is equivalent to solving a polynomial optimization problem. And so, you have the John-Fritz equations or the KKT equations if you have some boundaries, and then it ends up just solving a system of polynomial equations. And so this is something that that we have, that I would say the applied algebraic geometry world has really spent a lot of time on the last 30 years is how do you solve systems of polynomials equations quickly and efficiently? And some of the ways to do that belong to this group of polynomial homotopy continuation. And it's quite effective. There's still a long way to go, right? Because solving polynomial systems is hard, right? We've gotten so good at solving linear systems, but polynomial systems are still hard. But still, there's been a lot of progress, and so we can play around with the things that are implemented and see how far we can get. And so, again, the main idea is that you're going to minimize this distance between some data and some model. Minimizing the Euclidean distance is a polynomial optimization problem, and we can do this with polynomial homotopy continuation. And so just to give you a sense on the biological models, right, we were able to actually use some real data and use this model selection algorithm to decide between two different models of phosphorylation, and that you do see some nice results. And so this is running it over and over again for different parameter values, and this is the output. So we've had some success using a numerical algebraic geometry approach to model selection. And so now we want to try to use that same approach, but for these Gaussian mixture models. And we're not going to be able to use the same approach, out of the box. We're going to have to do a lot of different things to make the problem look like our other problem. So I alluded on the previous slide that we want to minimize the distance between the data and what I was calling the model variety. For us, it's going to be a model, and we're going to see what that will be. But I didn't want to put on this slide, right, because what our polynomial equations are, because for us as computational algebraic geometers, right, we are very concerned about the polynomial system. We like to see what that polynomial system is. We want to know if there's structure in that polynomial system that we can exploit. So mainly, if we use sort of Lagrange multipliers, we can write down the equations that we need to solve. So if I have, let's say this is my data point, and this is going to be my points on like whatever variety that I'm looking at, this is what I want to, this is the function that I want to minimize. And so if X is actually a local minimum of that, then we know that there exists some lambda such that X lambda is a solution to this system of equations, where these are the gradients of each of your polynomials here. For us, when we're going to look at the Gaussian graphical model case, we're going to have a single polynomial here, which is going to make it a little bit easier for us. All right, but that's what our polynomial system looks like. In general, if you want to get an idea of how hard these are to solve with polynomial homotopy continuation, a way to get a rough degree is to multiply the degrees of each of the equations that you get, and that can give you an idea of how complex the problem will be.
Sorry, what is the model variety in this problem? I mean,
I have not told you yet.
Okay. And how about x hat? What is x hat?
So x hat will be your data. And I also have not told you those two things. So here we're introducing the language of data and model variety, but I have not told you what those are going to be for this problem. And actually, we're going to need to finesse some things in order to get it into this language. All right, but that is the fantastic question, and that's the question that I want us to be holding into our head. So in polynomial homotopy continuation, so this was a very nice image. So actually, there's going to be an AMS short course at the joint math meetings, had run by a couple of people that really work in in sort of numerical algebraic geometry. This is a very nice image from that short course advertisement, because I think it sort of encapsulates everything with polynomial homotopy continuation in a single slide. And so for those of you that haven't seen polynomial homotopy continuation, the idea is you start with some, so let's say my system that I want to solve over here. Let's start with a pretty easy system. So I have a parabola and a circle, and I want to find their intersection points. And so the idea is this is the system that I want to solve, is my target system. So you have a little bullseye to tell you that it's the target system. And then you're going to start over here with an easier system to solve. So maybe, a super easy system to solve that I don't even need to use any tools for. Okay, sorry, there's a delay here. So what's almost like my simplest solution, I can do x squared minus 1 and y squared minus 1. And that's going to have 4 solutions over here. And then what you do is you create a homotopy going from this system to this system, and you track your, in this case, I'm going to have 4 of these are going to be my start points. And I'm just going to track them using predictor corrector methods going from here over to here. And then lots of things can happen as I do that. If I have 4 solutions here, I think I probably have 4 complex solutions here. What will happen is all 4 of these will end up on this side, and I will get them. You can have other behavior happen where multiple points. So if I had a solution that was a double point, 2 of these solutions would go to a same point over here, or you might have solutions that go up to infinity. And so that's the main, so you guys just learned about polynomial homotopy continuation in a single slide. And so this is the underlying machinery that we're going to use. All right, so now I want to get to Ali's question, which was, what are we actually going to do? So the main idea that we're going to do, there's going to be 2 things that we're going to do. We're going to fit the model, and then we're going to use a smoothing spline. And so the main thing, I'm going to use this language of a smoothing spline quite a bit. You have some data points. You're just trying to find, a piecewise cubic polynomial, right, that fits your data. Well, you have some parameters that you can control. You have this lambda parameter that's going to tell you this trade-off between fidelity to the data and the roughness of the estimate. So you have some control about how smooth you sort of want this piecewise cubic polynomial. But the main takeaway, when I say a smoothing spline, you're going to think piecewise cubic polynomial. So let's actually look at our problem. All right, and so this is where I have a blank slide, just because I want to get an idea of what we're doing here, because it's a little bit tricky. Okay, so we have, okay, I'm going to think about the one-dimensional case here. And I'm going to think about, okay, I have a bunch of data points. I'm not drawing them very well. Let's say I have a bunch of data points. And then what I'm going to do is I'm going to fit, I'm going to say, okay, EM algorithm, I'm going to say I have 2 clusters. And what the EM algorithm is going to do is going to sort of estimate some sort of mixture, Gaussian mixture density based off of the data that I put in. And so this is going to be part of the thing that this is going to form my data points, and I'm going to show you how this is going to work. So then we're going to do two sort of estimations going on. So first, this is our output from the EM algorithm. And then what I can do is for each of these data points down here, I can say, okay, where are they going to appear in this density? And I'm just sort of going up, right? And I'm taking all of these points. And then once I take these points, I'm going to do something else. Then I'm going to fit these points with a smoothing spline. And I have another picture on another slide if this doesn't become very clear. So I'm going to, and a lot of the times, if this is a good fit, if this two cluster model is a good fit, my smoothing spline will be pretty much close to it. But if it's a bad fit, what will happen is, imagine I don't have a bad fit might mean I don't have a bunch of points right here that correspond to the mass, but they're more spread out. And so if they're actually more spread out, what will happen is when I do my smoothing spline, I'll do that in purple. It's going to look a little bit different than my fitted model. And these are the things that we're going to compare. And so maybe this compared to this. And so this is the underlying idea. And I'm going to make it more into details. I have some more pictures, but this is a little bit tricky of what we're doing. And this is actually coming from Adele, he's actually an engineer, and he does sort of these things all the time. So it's an interesting sort of setup. So then here's some pictures that are a little bit, I didn't draw them, so they're a little bit easier to see. So what's the main thing that we're going to do? I have, some data set. I'm going to split it into training and testing sets. I think having the curve here is a little bit misleading because your data is actually going to be one-dimensional. It's going to be on this line, but we have this this density here because if we're simulating, and this is from what we're simulating from. And so then what we're going to do is we're going to fit the Gaussian mixture model with a different number of clusters, okay? And then I'm going to do that process that I did here. So once I have the GMM fitted to 2 clusters, 3 clusters, 4 clusters, 5 clusters, I'm going to take my test points and I'm going to see where they lie on that density, all right? And then I'm going to fit a smoothing spline to those points. Okay, and this is given to us in cubic polynomials. And so now what's going to be my test data, and we had this language from the other slide, which was my model variety versus my data. And so what is going to be my data versus this model? All right. So now what I'm going to do, I split it into blue and red. So now for my test set, for let's say the red points here, I'm going to actually compare the difference that I see on this curve, on this this smoothing spline compared to the actual model, the value of that point on the model here. And then I'm going to add up those distances. Okay. So this would be like the GMM with 2 clusters, which I don't have the picture of, but you can sort of imagine here, is going to be the model. And then the test is going to be, okay, where am I on this smoothing spline? And I'm going to compare. And we're not just going to do distances like we did in the other project. What we're going to actually do is this area-based method. And so this actually comes from Adele. He's used this area-based method in other sort of things where you're checking the distance between 2 different ways of fitting the data and seeing what is happening. And so this is actually the area that we're going to compute for each of the things. And so this ends up being the minimum distance of the test point and the spline. So the test point is going to be, okay, I had my test point. I'm going to see where it is on the fitted GMM model. Here's my spline. I'm going to use numerical algebraic geometry to get this distance. Okay. And then I also can just look at the y-axis distance, which is the error. Okay. And this is going to give us an area. And so then we can see how well this works. And I'm sorry, I had a little bit issues with my PDF, but so this looks a little bit weird, but you can get an idea of where the curve is. And so we've, played around with this. And so this might be something from this is a simulated data, and we do this process. And then what will happen is that some of that areas, as we get to the correct clusters, is going to go down. It's going to get better and better. And so here, we have bigger and bigger numbers, and then here we see a point where it starts to stabilize, and that's going to be how the k that we choose. So we would choose k equals 3 here. And so we can play around with this a little bit. And so here are some more sort of simulated data. This one is like 1 dimension with 3 components. This is a little bit, but can you guys see my cursor? Because I'm using my cursor on my computer. Okay, so this is a little bit fuzzy, but you have 2 dimensions and 3 components. Here's 3 dimensions, 3 components, but we're sort of projecting, and then 5 components. And so each of those actually work very well. And what we found with this area based approach is that we're basically getting the same results as AIC and BIC. Oh, sorry, I'm on, yeah. I should actually be on this slide, but that's okay. I can set us up here. All right, so because we did try it with this data, even though I have a different label on here. All right. And so we were getting similar results as AIC and BIC, which is the other way that you would do model selection in this case. We want to look at one quick approach, and I know that I'm approaching the end of the half hour here, but this will go pretty quickly. And so that was our area-based approach that we liked and was, but then we wanted to play around a little bit more. And so another approach is to do a local maxima approach. This one you need an assumption. So if I'm mixed, one of the interesting things mathematically about Gaussian mixture models is if I mix k components, like k of them, I don't always get k maxima. All right. And so there's been some very interesting work in this, some of the questions that you can ask is like, what are the range of different maxima that you can get if you mix k components in like d dimensions? And that's a very open problem, and it's actually quite hard to understand. But in a lot of the cases that we see in a real setting, you do have this condition that holds, that if you're mixing k components, you have k maxima. And so if we work under that assumption, we wanted to try this local maxima approach. And then in this local maxima approach, what we're doing is we have our data here, right? And then we're just going to do a kernel density estimate, and then we want polynomials. And so if I do a kernel density estimate, I won't get polynomials out. But if I then approximate that with a smoothing spline, I do get polynomials out, which allows us to do our things. So then I approximate it with a smoothing spline, and then I can actually find, the maxima using numerical algebraic geometry again. And so the main approach is you're going to, get this kernel density estimate. You're going to fit a smoothing spline. You're going to find all the local extrema. And actually, we don't use the John Fritz equations here. Sorry, this is a typo. You're just doing this like, setting the derivatives equal to 0 problem. All right. And then what we find though is that, since you've split it with this piecewise cubic function, you might have like some false maxima. And so to filter that out, we use the determinant of the Hessian to determine whether or not we want to count it as a good maxima or not. Basically, if it's small, we're not going to count it as the maxima. And so these are some results to give you an idea. So if like my n is 5 and I'm in one dimension, that means that I need to solve 500, basically 500 quadratic polynomial systems. All right, and I need to do that over and over again. And since it's small degree, numerical algebraic geometry actually handles that pretty well. And so, we tried this with some, and in all of the cases that we have here, both BIC and AIC and this approach picked the correct number of components. Where we saw some improvement was when, one of the things that you want with statistical methods is you do want it to be a little bit robust to the violation of the assumptions that you're making. So let's say you had a mixture of non-Gaussian, models, but they were like close enough, you would still want to get good results. And so this might happen when you're dealing with real data, right? That assumption is not perfectly, met, but if you have some variation, you do want the method to still spit you out reasonable results. And so here's some engineering data. So these are measurement errors from auto manufacturing assembly line to identify in control and out control sub-assemblies. The experts here, said that there's really two components. And so when we're running this, we're getting two components using this local maxima approach. And then we can also see for this like non-Gaussian mixture models, if I really simulate from non-Gaussian, how well does it do? And then we can see, okay, let me give you these examples is like two components, 3 components. And so you really want to see this 2, 2, 3 here, so that the area-based algorithm had a little bit of trouble pulling out the 2, 2, 3. The local maxima approach did the best, and then AIC and BIC tends to overestimate the number of components, especially if that Gaussian assumption is not satisfied. Okay, so I'm going to end there. I'm going to give you a little bit of a lay of the land here. So this work that we've done is really from this paper here, and then this was the other paper that I talked about with biological systems. But in algebraic statistics, Carlos Amendola and Jose Rodriguez have been doing some very interesting things using these moment systems. So if you're really interested in that, that would be some other references that you can look at. All right, so I will end there.
Thank you. Any question for Elizabeth? I have one actually.
Yeah.
Sorry, is there any upper bound on the degree of the polynomials in terms of the data? I mean,
yeah, because we're always working with these smoothing splines. They're always cubic, and so we're always with cubic polynomials, and that's what makes this work and makes it work fast, because if we were going up in degree, it'd be a lot harder. So yeah, so that makes it work fast. The problem is if you're going up, we can do this if you're putting like a smoothing spline, you're splitting up the regions, right? And so in one dimensional, this is reasonable. In two dimensionals, it's sort of, you have this rectangular grid, all right? And three dimensions, you're starting to push the limits of like, oh, you're going to have to do so many, even though you're solving these cubic systems, you have to solve so many of them that it might not become reasonable. And so then our question for, to go back to the people that work in numerical algebraic geometry is like, oh, okay, how can we do this faster?
Right.
Here's the application. Now let's do it faster.
Right. And maybe my other question is, just because you talk about the number of components, then that also reminds me of the techniques in topological data analysis. Do you think there is any connection between what you did here and also?
I don't know if I think it would be like a different approach with topic, because I can imagine, I don't know for sure, but like I've been to enough topological data analysis talks that I can imagine what they would be doing there. And so, yeah, I don't know if there's like a direct mathematical, I think it's just a different approach.
Right. Okay.
Right. And so, yeah.
Okay.
I don't immediately see a connection there. That doesn't mean that, that there isn't a connection there, but there might be.
Okay, thank you. Any other question?
Yeah, I have a question. Yeah, thanks for the talk, Elizabeth. I just wanted to make sure I understood. You said that the model that's recommended using these like area-based sort of residuals is the same model that's recommended by the different information criteria that are like standard.
Yeah.
Is this to say that like just doing a naive residuals and minimizing the sum of squares does not give like consistent results?
I think we started trying that. For some reason, the area-based method worked better. We compared with like, okay, so if I have this, I think you're asking about this picture right here, right? Like, so if I sum up these ones, like it still did it. It was just with the area, we got like sort of a little bit, the signal was clearer. So this would still pull it out, but like we got better signal by adding the area.
Interesting. Do you have like any intuition why that might be the case, or is this just engineering?
This is just engineering.
Interesting.
Yeah, so it was just something that like I know that Adele had used a similar approach in other of his papers, and it found that it worked better, like that you get better signal from using this area. Why it works, I don't think any mathematicians have gone back and figured out why that is.
Cool. Very, very good to know. And also in that table where you were giving the values of n, was n the sample size that you are requiring?
Yeah, n actually here was the total sample size, and then you're splitting, you're talking about this,
Yes, thank you.
I actually think that this n is our test size, so the sample might be like because we were splitting it like 2/3 and I want like, just because I'm looking at the number 500 there, I feel like that was our test size. I mean, our training size. And then we had a little bit more we probably split it half and half. So our total would have been 1,000, and then 500 would have been our training.
That seems, I mean, naively to me, that seems remarkably high of a sample size that you need to perform well. I'm not like super familiar with the problem, but I mean, is this like competitive with other methods in terms of efficiency?
Yeah, so that's a very interesting question, because I don't think we actually played around with like varying the number of n, like, because what we were more interested in was the complexity going the other way. Like, it's actually easier for us if this number is smaller, because then we're solving a lot fewer systems. So I think we were more interested in seeing how far we could push it this, in the higher direction.
Oh, I understand. So I see.
So, but that's a great question. I mean, I don't think we even checked with like smaller numbers, because we were more interested in like, what are the like limitations on that upper end. So but it would be interesting to go back and actually just like, we have the code, simulate, and just see. It'd be very quick. Yeah.
So like 500 is what the maximum number of equations in your system that you can solve, or like what are you like trying to guarantee with this?
Yeah, like at what point does our computer start slowing down, right? What point am I getting, like with 500 and cubics, I'm actually probably getting it back in seconds, right? When I'm getting up to here, with like these 5-dimensional systems, then like this is probably like the limit of, okay, I don't want to wait anymore for the computer. So like really, as the dimension goes up, your complexity goes up quite a bit.
I understand.
Yeah.
Great, thank you. That helps.
Okay, any other question? Okay, if not, let's thank the speaker again, and thank you all for coming to this session, and hopefully I see you next week. Have a pleasant rest of the day. And thank you, Elizabeth, for coming and giving a talk here.
Thank you, guys.
Yeah, I guess I will see you in JMM, like maybe in a month or so.
I won't be there, but my
Okay.
part will be there. And there'll be lots of interesting people there. So,
All right.
all right.
Thank you. Have a good day. Thank you.
Bye.